Hello all, in this video we will take a look at some of the properties of the subgradient that will be useful in establishing various kinds of bounds. We are considering problems of the form x star equal to argmin over x in calligraphic x f of x, where f is convex and calligraphic x is closed convex with calligraphic x belonging to relative interior of the domain of f. We have already seen two types of optimality conditions for this problem when f was smooth. When f is non-smooth, the optimality condition must be stated in terms of the subgradient of f. The problem can be rewritten as x star equal to argmin over x, f of x plus indicator function of calligraphic x at x. Then the subgradient of the objective is given by subgradient of f plus indicator function at x is subgradient of f of x plus the norm cone of calligraphic x. We recall that subgradient of the indicator function was the norm cone. So here we have a sum of two sets. So we get the optimality condition that 0 belongs to the subgradient of f of x star plus norm cone of x star. So on the right hand side we have the sum of two sets. Another way to write this equation is that there exists a gx star which is a subgradient of f at x star such that minus g of x star belongs to the norm cone of calligraphic x at x star. Next, let us look at the conjugate subgradient theorem. Suppose that f is proper and convex and f star is the conjugate of f. Then there exist x and y such that the Finchal inequality becomes an equality, which is that x comma y inner product is equal to f of x plus f star of y. So for these x and y, it turns out that y is a subgradient of f at x. Additionally, if f is closed, then equivalently we also have that x is a subgradient of f star at y. To see the proof, note that the condition that y is a subgradient of f at x is equivalent to the first order condition, which is that f of z is greater than or equal to f of x plus inner product of y comma z minus x, which is equivalent to y comma x inner product minus f of x greater than or equal to inner product of y comma z minus f of z, which is an inequality which holds for all z, and therefore equivalently it also holds when the right hand side is maximized over all z. So maximizing the lower bound with respect to z, we would obtain f star of y. So we would obtain that f of x plus f star of y is less than or equal to inner product of y comma x. Now if you recall the Finchal inequality, this inequality is the opposite of that inequality. But Finchal inequality is generally true. So the only possibility is that the equality holds. That is, the inner product of x comma y is equal to f of x plus f star of y. So in other words, we have established that if y is a subgradient of f at x, then this equality holds. Now additionally, if f is closed, we have the Finchal-Mohu theorem, which said that f star star, the biconjugate of f, is equal to f. So let us just denote f star with g. So then the same equality can be written as x comma y inner product is equal to g of y plus g star of x. Then we have already established that x is a subgradient of g at y, and therefore it is also a subgradient of f star at y. So to summarize the conjugate subgradient theorem, we have seen that if f is proper closed and convex, then the equality x comma y equal to f of x plus f star of y is equivalent to saying that y is a subgradient of f at x, which is equivalent to saying that x is a subgradient of f star at y. So how does this help us in practice? It says that to find the subgradient of the conjugate function, we only need to solve the maximization problem. That is, that the subdifferential of f star at y is the argmax set over x, x comma y minus f of x. without actually needing to evaluate f star. Likewise, we also have that the subdifferential of f at x is the argmax set of over y, x comma y minus f star of y. So in situations where these problems are solvable and are in closed form, it would be easy to find the subgradients of f and f star by solving these equations. The chain rule for subgradient calculation for composition with differentiable functions is very useful. It says that for h of x equal to g of f of x, where g is differentiable, the subdifferential of h of x is given by g prime of f of x times the subdifferential of f at x. Actually, similar rules can also be derived if f is vector valued. As a simple example, consider the square distance of a point x from the set calligraphic x. So phi of x is given by half of distance square of x comma calligraphic x, which can also be written as min over u in calligraphic x, half of norm square of x minus u. If you recall the definition of the projection, this can also be written in terms of the projection operator as half of x minus px norm square, where recall that px was argmin of u in calligraphic x, norm square of x minus u. The subgradient of the square distance function can be calculated in a number of ways. One easy way is to use the envelope theorem, which says that the subgradient of phi of x is x minus px. We can use this formula to calculate the subgradient of the distance function. Note that the square distance function is the composition of half of square and the distance of x with calligraphic x. Therefore, by chain rule, we have that subgradient of phi of x is equal to distance of x comma calligraphic x times the subgradient of the distance of x. Therefore, the subgradient of the distance of x is equal to x minus px of x divided by distance of x comma calligraphic x. So later we'll look at an example where we will use this result. Now we come to a very important property of the subgradient, which is that it may not be a descent direction. That is, unlike the gradient or the projected gradient directions where we were able to establish the descent property, here in fact it is possible that the function value could increase in the negative subgradient direction. Let us look at a counter example to show that the negative subgradient is not necessarily a descent direction. For that, consider a function in R2, which is that f of x equal to absolute value of x1 plus 3 times absolute value of x2. Then let us consider the point z equal to 1, 0. So that f of z equal to 1. The subdifferential at that point is given by, you can verify that, it is given by 1, u, where u is between minus 3 and 3. We will take the step of the form z minus eta g, where g is a subgradient, and then look at the function values for small values of eta. So let us first consider the subgradient g1 equal to 1, 0. You can see that if we take a step in the direction minus 1, 0, then z1 will become 1 minus eta, 0, and the function value at z1 will be equal to absolute value of 1 minus eta. So for eta small, this quantity will be less than 1, and therefore f of z1 is less than f of z. So this particular negative subgradient direction is in fact a descent direction. But if you consider subgradient g2 equal to 1, 3, then the new point will be z1 equal to 1 minus eta, minus 3 eta. Therefore f of z1 will be equal to absolute value of 1 minus eta plus 3 eta, which is a quantity which is greater than 1 for all eta. So the function value increases along minus g2, and therefore minus g2 is not a descent direction. So a negative subgradient direction is not necessarily a descent direction, no matter the choice of eta. We can have a look at the contour plot of this function. As you can see, the subdifferential of any point along the axis includes directions such that the function value if I take the negative subgradient direction, would increase. From this figure, you can imagine that in the same way, I can consider more and more skewed functions for which the negative subgradients will be ascent directions. So even though there may exist a descent direction, it is not necessarily easy to find one, because generally we cannot search over the subdifferential set. In fact, our oracle assumption is that the oracle provides us with a subgradient and not the full subdifferential set. So why to use the subgradient if it is not a descent direction? One reason is that there is a very useful property that its distance from the optimum set still decreases. If we are initially at a point z, then its distance from the optimum is 1. So I have drawn a circle depicting that. You can see that no matter which subgradient is selected, if eta is sufficiently small, I end up remaining inside the circle. In other words, any subgradient still results in the distance from the optimum to decrease. Let us look at this so-called descent over distance property more rigorously. To see this, let us assume that we are in an inner product space. Let us denote x plus equal to x minus eta subgradient of g at x. Then norm square of x plus minus x star is equal to norm square of x minus eta gx minus x star, which is nothing but norm square of x minus x star minus 2 eta inner product of gx comma x minus x star plus eta square norm square of gx. Then using the subgradient definition, we have that norm square of x plus minus x star is less than equal to norm square of x minus x star minus 2 eta f of x minus f of x star plus eta square norm square of gx. Here you can see that as long as eta is sufficiently small, that is eta is less than equal to 2 times f of x minus f of x star divided by norm square of gx, then we have that x plus minus x star norm square is less than equal to x minus x star norm square. So in this proof, we did not even require that x star be unique. So the subgradient is actually getting us closer to any x star that is in the optimum. So that is all for this video. In the next video, we will analyze the oracle complexity of subgradient descent algorithm.